Hello and welcome to another session of Introduction to Astrophysical Fluids. In this session, we will discuss the physics of Jeans instability. Jeans instability is one of the most important instabilities in the framework of astrophysics. Because often the stars and the galactic chunks are believed to have been formed as a result of Jeans instability. Now, what does Jeans instability mean? So previously, if we remember that we have seen in the absence of any body force and viscous effect, any weak perturbation of first order in a polytropic fluid for which the pressure is just only a function of density, always, and actually has a relation like P is equal to some constant times rho to the power gamma, this type of fluid always leads to an acoustic wave mode which repairs the perturbation given the initial state is a static, the state was in hydrostatic equilibrium. Now, in the context of astrophysics, often we can see systems under the influence of gravitational field. So we can no longer neglect the body force effect. So the body force and viscous effects both were neglected in the previous case where we just saw the emission of sound waves or the formation of the sound waves in order to respond to any weak linear perturbation made to the system. But in astrophysics we have to consider the body force, which is the gravitational field. And if the system is with a large mass like a star forming cloud, for example, then the system is acted by its self gravity. So the system is acted, the body force is nothing but its own gravity, own field of gravity. So now the question is that does such type of system also lead to lead to the stability and linear mode of like sound wave or something like that, or this leads to any type of instability in this case, even if one starts from a hydrostatic steady state? That is the question. Now, in order to answer to this question, let us first consider the set of governing equations. So the set of governing equations, the first one you all can now recognize, this is the famous continuity equation, del rho del t plus divergence of rho v is equal to 0. This is the famous Euler equation, of course, because we have neglected the viscosity. So del v del t plus v dot nabla v is equal to minus gradient of p by rho minus gradient of phi. So here, as you can easily see, that we have neglected the viscosity, so this is nothing but the Euler's equation. The third equation is the Poisson's equation for gravitational field. So nabla square phi is equal to 4 pi g rho. Here you can easily see that phi is the gravitational potential. So g, small g, which is the gravitational intensity, can be written as minus gradient of phi. Now Jeans assumed that the unperturbed state is a uniform fluid medium with infinite extent. And this state is at rest. Uniform means the density and pressure, they are constant everywhere. Pressure is constant because we have assumed a polytropic, which is a special case of a barotropic fluid. So where rho is a function of P only. So if rho is constant, then if rho is constant, that means rho 0, then P is also having a constant value which is equal to P0. And the fluid is at rest, that means V0 is equal to 0. So that is the unperturbed state. Now the problem is that, so a priori, I mean, you can see that if you just insert this initial condition in this set of equations, you can easily see that if the this state is steady, so the initial state should always be steady. That I said at the very beginning. Okay, and in addition, it is now uniform and static. So del t's are all 0, v is 0, so this is the continuity equation trivially vanishes. This term is 0, this term is 0, this term is non-zero, minus gradient of p0 by rho 0 minus gradient of phi 0 is equal to 0. So that is the unperturbed state. We have not yet injected these conditions. We have simply said that if the initial state is steady and no, just a minute. So we have basically injected this condition but not the uniformity condition till now. That I am coming later. So if our system is steady and static, then what happens? The system can so this one is 0 and this one is 0 once again, this one is 0, so this one is exactly equal to this one. Okay, so the sum of these two terms will give you simply 0. Okay, so finally from that you can write gradient of p0 is equal to minus rho 0 gradient of phi 0. Okay, and nabla square phi 0 is equal to 4 pi g rho 0. Okay, so that is the last one, that is the Poisson's equation. So phi is phi 0 and rho is rho 0. Now my question is, it looks fine, right? Now the question is that if you see in depth, is it still okay? Well, there is a catch. The thing is that this is not fine. That means the equations are not auto-consistent, self-consistent. Why? Because if you now consider for that the system, the medium is uniform, then the medium will have a constant non-zero value for rho 0. Okay, so rho 0 will be non-zero but constant. Okay, and if we have barotropic or polytropic fluid, then P is also constant. So P0 is constant. So rho 0 constant means P0 constant, and P0 constant means gradient of P0 is 0. If rho 0 is non-zero and gradient of P0 is 0, then gradient of phi 0 is also 0. That means phi 0 is a constant. So if gradient of phi 0 is 0, now you remember divergence of something which is 0 is also 0. And that means that 4 pi g rho 0 is 0. Okay, that means rho 0 itself is 0. So we started by saying that we have a uniform medium, so rho 0 is constant but strictly non-zero because the matter should be there. But now we end up by saying that rho 0 is 0 everywhere. So what is the problem? Actually the initial unperturbed condition is not satisfied by a uniform infinite barotropic medium. Okay, that means that, I mean, up to this there is no problem in this equation, but after that this initial unperturbed steady static condition is not satisfied by a uniform medium. That means whenever you make the assumption that rho 0 is constant and non-zero, then the problem is started. Okay, and this is known as Jeans swindle. Jeans did not realize the fact, but he was the, I mean, how to say, like, he was the first one to address this problem analytically, and we will come to this later, and he actually somehow found qualitatively the same result. So what is the way out? In fact, one has to first solve the equation in A and then should consider the perturbation around it. So first we have to solve this set of equation and to check that which type of functions actually satisfies this set of equation, and we will see that rho 0 is constant and non-zero can never be a solution of this equation. Okay, so that is the proper way. But very interestingly, historically, when Jeans finally analyzed his thing, it is found that the stability condition what Jeans obtained actually remains qualitatively the same if we do it properly from a well-defined initial state. Okay, so that is the proper way of treating that. Okay, then in case you can just remember Lane-Emden's equation. Actually in this case one has to like solve Lane-Emden equation type of thing, which is the spherical for a spherical system this type of equations can be cast into this Lane-Emden type of equation, and one can actually see this type of the solution of this problem in a proper manner. But here for this discussion, just for the sake of simplicity, we study the original treatment by Jeans. Okay, that means we will use the Jeans-Swindle method. Okay, now after perturbation, what happens? So why we are following this Jeans-Swindle method? Because of two reasons. First one is that this is historically important to know what Jeans did, and finally it is simple and gives qualitatively the same result as that of a mathematically properly done method. Okay, now after perturbation, what happens? V is now becomes V1, rho is now becoming rho 0 plus rho 1, and P is to P0 plus P1, and finally phi is also equal to phi 0 plus phi 1. Okay, again we obtained the linearized equations as del rho 1 del t plus rho 0 divergence of V1 is equal to 0, rho 0 del V1 del t is equal to minus CS square times gradient of rho 1 minus rho 0 times gradient of phi 1, where CS square is nothing but the polytropic sound speed. Now you know this is nothing but gamma P0 by rho 0. Okay, and finally you have nabla square phi 1 is equal to 4 pi g rho 1. Okay, now we have three equations and three perturbation variables. One is rho 1, one is V1, one is phi 1. Okay, the P1 is actually replaced by the polytropic condition by rho 1. Okay, in the next step we consider very simply plane wave solution for the weak perturbations, all weak perturbations. So rho 1 will be equal to some rho 1 0, which is the amplitude part, times e to the power I k dot r minus omega t. This is the plane wave type of solution for the fluctuations. Another way of saying that as they are linear, then we can think them of to be composed of Fourier components. Okay, and then we take one of the Fourier components. Okay, another way just to say that we are assuming that plane wave solutions where V1 will be equal to V10 e to the power I kr minus omega t, and then phi 1 will be equal to phi 10 e to the power I k dot r minus omega t. Okay, then finally we replace all these three values in this equation. Okay, all these three expressions, okay, this plane waves type of solutions, and we will obtain that minus omega rho 10 plus rho 0 k dot V10 is equal to 0 minus rho 0 omega V10 is equal to minus C square k rho 10 minus rho 0 k phi 10. Okay, k is the once again the wave vector corresponding to the perturbation. And finally the Laplace equation or the Poisson equation actually for gravity gives minus k square phi 10 is equal to 4 pi g rho 10. So we finally have a set of 3 algebraic equations with 3 unknowns, rho10, v10 and phi10. Of course we have 5 unknowns because v10 is a vector quantity, so you know that actually we have 5 equations, 5 scalar equations and 5 unknowns. Okay. Now take a dot product of C, okay, with K. See, if we just take K dot in the both sides of C, this equation, the second equation, okay, then and finally we eliminate K dot V10 from B, or using B. Finally we get another expression, which is the expression number E, which is omega square rho 10 is equal to CS square K square rho 10 plus rho 0 K square phi 10. Okay. Finally, I have D and E. Okay. D and E, I just have two variables, phi 10 and rho 10. I have got rid of the V10 variables. Okay. So, combining, we get omega square rho 10 is equal to CS square K square rho 10 minus 4 pi G rho 0 rho 10. And then, just rewriting, we can get omega square is equal to Cs square times K square minus Kj square. Here I define this Kj square such that Kj square is equal to 4 pi G rho 0 by Cs square. Okay, and this is known as the Jeans wave vector. Okay, and here you can actually see this is nothing but the dispersion relation. Okay, for the plane wave solution corresponding to the perturbation. Okay. Now clearly, when k is greater than kj, then omega is real because omega square is positive and the system will respond through linear wave mode. If k is less than kj, then omega is imaginary and the system then will be led to instability, and which is called the Jeans instability. Okay. Now, before discussing further, let us try to understand what leads to instability here actually. Okay. So, whenever the density of some region under self-gravity is increased, the fluid pressure gradient would try to repair it just like in a normal compressible fluid. But when the density gets higher, it creates a stronger gravitational field, self-gravity field will be increased. Okay, that's true, that is by Poisson's equation. And that further rise, that leads to the further rise in density. And that actually leads finally to an instability due to gravitational collapse. Okay. In fact, if the size of the perturbation L is greater than the Jeans wavelength, which is defined as lambda j, which is nothing but 2 pi by kj, then the increase in self-gravity dominates over the increase of pressure, and which is leading to the Jeans instability. Okay. Now, analogically, for the size, there is a critical value of mass, okay, for which Jeans instability takes place only if the mass overcomes or mass dominates over exceeds the value of mj, which is nothing but 4/3 pi lambda j cube rho 0. This is called the Jeans mass. Okay. Now expressing the lambda j in its previous expression. So kj is this, and from lambda j 2 pi by kj. Finally, you can also write this equation. This basically shows you that mj is equal to 4/3 pi to the power 5 by 2 gamma kbt by gm whole to the power 3 by 2 times 1 by rho 0 to the power half. So mj is proportional to t to the power 3 by half, and it is also proportional to 1 by rho 0 to the power 1 by half. Okay, why is that? Just try to understand physically. That is my question to you. So in a nutshell, if a perturbation in a uniform gas involves a larger mass than mj, then the local gravitational collapse will set in, and that actually leads to Jeans instability, thereby fragmentation of the whole system into piece. So local gravitational collapse basically makes the total continuous mass system to be fragmented, if you can understand the whole picture. The stars and galaxies are believed to be the outcomes of such instability, but interstellar mass with hydrogen atomic density nearly one particle per cubic centimeter at temperature 100 Kelvin gives a Jeans mass which is of the order of 8 into 10 to the power 38 gram, which is much larger than the typical mass of a star, which is of the order of 10 to the power 33 gram. It is then assumed that the Jeans instability first breaks the interstellar matters into larger galactic chunks, and then further breaking by other mechanisms gives stars. So this is not just one step Jeans instability which can give us the usual stars, okay, but this is a two-step process. One step is the bigger interstellar matter, then this breaks into chunks, larger chunks, and from that larger chunk, that is of course by Jeans instability, but then from larger chunks how they get further fragmented, that is another interesting issue in astrophysics. Okay, so that's all about Jeans instability. Okay, thank you very much.